In this section, we want to start talking about relative sizes of atoms and ions. So what is the radius of the atom? Thinking about an atom, they're really, really, really small, okay? But we want to be able to compare the size of the atoms to each other because the size of atoms factors into how they behave, how they form bonds with each other, how they overlap with each other, etc. And we need you to understand the relative size of them. You will need to compare and contrast radii or the radius for neutral atoms, anions, and cations. There are rules we follow, there are general trends, but if you understand the why, you'll have a better time in this section than you will if you just memorize the trend. So for general objectives here, you'd be able to use electron configuration effective nuclear charge to be able to predict the relative size of the atoms. If you understand why, it's going to be easier. Coulomb's law factors into this. Some of this stuff is actually for the next section. I'm sorry, I didn't have time to take this slide out, and now that it's on my iPad, it's harder to adjust the slides, but things like ionization and electron affinity will be in a different video. So, atomic size. First, atomic size decreases as we go from left to right across the periodic table. So across the table, it's going to decrease in size. Which I guess the better way to write that is like it increases this way. This is because of increasing nuclear charge. So let's look at lithium versus neon. Lithium, electron configuration, 1s2, 2s1. The Z here is 3. Remember, Z is your nuclear charge, and it's equal to the number of protons you have in your nucleus, or the number of protons that the atom has. Neon, on the other hand, 1s2, 2s2, 2p6, and Z is equal to 10. Now, lithium has 1 electron in its second energy shell. Neon has 8 electrons in its second energy shell. So they're both filled to the second energy shell. What I mean by that is if we think about it in the Bohr model, one and two, lithium has 2 electrons in the middle, or in the first shell, 1 electron in the second shell. It's got 3 protons in the center here that are pulling on those electrons. Neon, on the other hand, has 10 electrons here, pulling on 1, 2, 3, 4, 5, 6, 7, and 8, pulling on 10 electrons. These 8 electrons in the second shell are the same relative distance away from the nucleus as the 1 electron in lithium. But I now have 10 protons in that center that are pulling on those electrons. It's hard for students to correlate this and understand this because it's still, 3 electrons to 3 protons here. 10 electrons to 10 protons here. And people are like, but it's a 1-to-1 ratio. It is a 1-to-1 ratio. But if you think about the relative distance of them, when you've got, lithium in the center with its 3 protons, and then pulling on just 3 electrons outside, the 3 electrons cannot pull as hard as the 3 protons in your nucleus can't pull as hard on those 3 electrons as 10 protons can on 10 electrons when they're an equidistant away from the nucleus. So just the fact that there's 10 protons in the center makes that nuclear charge or that positive charge of the nucleus stronger. And even though it's pulling on an equal amount or same relative amount of electrons, it can pull it tighter. It pulls it closer together. And so neon will actually be smaller than lithium. Again, it's hard to think about, but pretend that you're in the center here, and you've got 10 people in the center here pulling on these 2 rings. 10 people pulling on 2 rings is stronger than just 3 people pulling on 2 rings. In addition to that, we do have this shielding effect. Electrons and protons like each other. They're attracted to each other. Opposite charges attract. But the electrons are repelling each other as well. Here in lithium, I've got this proton in the center, these 3 protons in the center that are attracted by these electrons. This electron out here is being repelled by these 2 electrons, even though it's attracted to the nucleus. Here, I have 10 electrons attracted to the nucleus that are only being repelled by 2 electrons. So it's more powerful on the outside too. It's kind of like, if you've got a circle of 10 people in the middle, your next circle out, and that's your nucleus. Next circle out, you've got a ring, and it can hold 2 people, 2 spots. Outside of that, you've got another ring, but it's only holding 1 person. That second ring out from the nucleus with that 1 person, those 2 electrons can block it a little bit better. Those 3 protons in the nucleus aren't strong enough to pull it too tight, pull it too close. But if I have that second ring out, and I have 8 electrons in that second ring, even though they're being repelled by those electrons in the first ring, it's 8 against 2 here. I mean, it's just going to be able to pull it tighter, pull it closer together. The pull from that nucleus is stronger, and the attractive forces from those outer electrons is stronger to that nucleus, and it's going to pull the molecule in tighter. On the flip side of that, atomic size increases going down the periodic table because the outermost electrons are in a higher shell. So if I look at sodium versus potassium, sodium has abbreviated configuration, neon 3s1. Potassium has an abbreviated configuration, argon 4s1. Potassium just has 1 more ring. It's just 1 spot further from the nucleus. So you got your nucleus, n equals 1, n equals 2, n equals 3, and n equals 4. Sodium has an electron. Its outermost electron is right here. Potassium, its outermost electron is out here. So as we add more shells into the atom itself, they have to take up more space. They have to go somewhere. So as we go down the table, it increases as well because we're adding to the number of shells that atom must contain. So atomic radius, it increases with increasing energy level down a group. It decreases as we increase the number of protons across a period. The additional protons exert a stronger attractive force on those electrons, drawing the electron cloud in and reducing that overall size. This trend follows pretty strongly. For the most part, you can follow this trend. There's not a lot of exceptions to this, so you can kind of look at this trend and go for it. I haven't told you guys this. The one way that I was taught to remember this is that this guy, francium, we call him Fat Frank. I was taught that to remember the biggest element is Fat Frank. And as of right now, he is the biggest atomic size we have. And then just showing you a little bit of a picture of it, how some of these can look, and how you can see they're getting really small, decreasing across the table into very small spaces, increasing as we go down. This one doesn't go down to Frank's row. Frank would be here. Or francium. I guess we should call him by his actual name. And I guess it's not a him either. It's just an element. But I like this picture because it kind of shows you some real-world comparison of the atomic radii to each other. So another just overall abbreviation here for atomic size. We see boron, carbon, nitrogen, oxygen, fluorine. If you look, these are all group 2, or these are all 2p. Right across the table from each other. So this has atomic number of 5, 6, 7, 8, and 9, respectively. And we see that the radius does decrease as we go across. And we see the electric configuration. This is for the, not all, but this is most of your valence electrons listed here. It's just missing your 2s1, or 2s2s. And then we see the same correlation going, so we see them getting smaller or decreasing left to right. If we go down the table, we see an increase in the atomic radii. And for that, it's because your valence shell is increasing. What about ionic size? Typically speaking, cations, or actually truthfully speaking, cations are always smaller than their own parent atom or their neutral atom. Anions are always larger than their parent atom. The trick to that is the words their parent. So cations are always smaller. That doesn't mean they're smaller than every parent atom. They're smaller than their own. And anions are always larger. So we can see some nice pictures here kind of showing this. Now, the reason for this, though, is think about what's happening here. If I form a cation, cations mean I lost electrons. So if I'm forming a cation somewhere and I've lost an electron, that means I have now one more proton in my nucleus than I have electrons in my atom. So for example, lithium versus lithium plus. Lithium has 3 protons, 3 electrons. Lithium plus has 3 protons, 2 electrons. So now, instead of it being a 1-to-1 pull, I now have one more proton pulling on less electrons. They're just going to pull it tighter. Now each electron feels more than the equivalency of an attractive force than they felt before, because they don't have to share with as many people. Anions, on the other hand, anions are formed by gaining electrons. And so we see here F to F minus, an increase in it. Well, if I go from F to F minus, F has 9 protons, 9 electrons. F minus has 9 protons, 10 electrons. Now I have the same number of protons trying to reel in a greater number of electrons. Each of those electrons will feel less pull than they felt before because that positive charge has to be dissipated over a larger number of electrons now. If I added two electrons to that, so like oxygen likes to be -2, it's going to get even bigger because now in oxygen's case, I would have 8 protons trying to pull on 10 electrons. It's just less positive charge to go around. And so this is written in my student notes, but not on the PowerPoint, so I'm going to write it here. For ions in an isoelectronic series, your ionic size decreases with increasing nuclear charge. What the heck does that even mean? Well, in the previous video, we looked at an isoelectronic series between O2 minus, F minus, Ne, Na plus, and Mg2 plus. What that means is that as I go from oxygen to magnesium, the size will decrease. So this will be largest, this will be smallest. Remember, isoelectronic means same electron configuration. Why does oxygen want to gain 2 electrons? So it can be like neon. Why does magnesium want to give up 2 electrons? So it can be like neon. everyone wants to be like a noble gas. Noble gases not only have completely filled subshells, meaning like neon has a completely filled 2s and 2p shell, but the n equals 2 shell itself is also completely filled, which is the maximum stabilization of energy it can have. So let's rank the following in order of increasing radius: chlorine, chloride ion, sodium, and sodium ion. Chlorine, we're going to write the abbreviated here, is neon, 3s2, 3p5. Your chloride ion is neon, 3s2, 3p6. It's the equivalent of argon. Sodium is neon, 3s1, and sodium plus will be the equivalency of neon. So if I'm thinking about this, technically sodium and chlorine really are in the same series. They're in the same energy level. But thinking about how many protons and electrons I have here, what do I think is going to be my overall trend? Well, I know that my sodium will be larger than my chlorine. How do I know this? Because they're in the same row. The trend is that it decreases as I go across the row, or it increases right to left, or it decreases left to right, whichever way you want to think about that. But since they're in the same exact energy shell, what that means is that the chlorine, 17 protons, 17 electrons, is going to pull tighter than the sodium, which is 11 protons, 11 electrons. So I know chlorine will be smaller than sodium. Now I got to think about the other things here, though. Sodium ion and a chloride ion. I know that cations are always smaller than their neutral atoms. I know anions are always larger. But where are they in relation to the other two neutral atoms I have? Is sodium plus, it's going to be smaller than sodium, but is it going to be smaller than chlorine as well? Or is it going to be larger than chlorine? Well, if I look at the electric configuration of sodium, it has the equivalency of just neon. Neon is in a lower energy level than chloride, or than the chlorine atom. Since sodium was able to get rid of that one electron in its outer shell, sodium plus will be lower, or have a smaller smaller radius. Its ionic radius is smaller than the atomic radius of chlorine, is what I'm trying to say. Chloride ion now has the equivalency of argon, which is going to be the end of that row, which is even smaller than sodium. So it's bigger than chloride. It's bigger than your chlorine atom, but it's smaller than your sodium. Go ahead and practice some of these in your book. They're Chem 101, notes, etc. Try to think about why these trends are happening and why we're seeing the results we are. If you think about where the electrons are residing, you'll have a better time with being able to predict these trends.